very good morning. Welcome you all to the NPTEL course on electrical distribution system analysis. And today we will be talking about emerging technologies and future trend in the field of distribution system engineering. Now, to start with, we will talk about multi-microgrid in distribution systems. Today, as we discussed that IIT Roorkee become one microgrid for me, and probably let us say there could be millions of microgrid that can be active across the country. So, in a particular geographical area, simultaneous operation and exchange of energy between two different microgrids become a future challenge. So, multi-microgrid MMGs are advanced systems that integrate multiple interconnected microgrids within a distribution network, and these systems enhance the resiliency, flexibility and efficiency of power distribution by coordinating the operation of local energy resources, exchange of energy from one microgrid to other, storage systems and controllable loads. Now, when we talk about coordination of multiple microgrids involves the coordinated operation of several microgrids and each with its own generation, storage and load management capabilities. This coordination can be centralized or decentralized depending on the system design. What is the benefit of having multiple microgrid applications? It enhances grid reliability and resilience by allowing microgrids to support each other during disturbances and optimizing the overall energy use within the distribution network. Means, let us say there are two distribution microgrids today at IIT Roorkee. One is the School of Artificial Intelligence and Data Sciences, the other is Electrical Engineering Department, where we have loads, PVs, diesel generator connected, main grid connected, battery energy storage systems. Now, let us say if one system fails, can the other system cater the energy requirement of the failed system? So, means can those microgrids become complement to each other, and if it is so, then certainly we do see there is a benefit out of multi-microgrid distribution systems. Now, there could be also a possibility of exploring energy management optimization, where advanced energy management systems EMS of these, that is multi-microgrids, use optimization algorithms to manage energy flow between microgrids, ensuring efficient operation. And these systems can employ techniques such as multi-agent reinforcement learning and cooperative multi-objective optimizations. And majorly we can see the improvement in economic efficiencies, which reduces operational cost and minimizes carbon emissions by optimizing energy use and storage across multiple microgrids. Now, resilience and fault mitigation. Multi-microgrids enhance the resilience of the distribution network by providing multiple layers of redundancy. In the event of a fault, microgrids can isolate themselves islanding and continue to operate independently, thus maintaining power supply to critical loads. So, through this process, it enhances the reliability of the power supply and reduces the impact of outages on consumers. Now, when it integrates with renewable energy sources, multi-microgrids facilitate the integration of distributed renewable energy sources, that is RES, such as solar PV and wind turbines. They can efficiently manage the variability and intermittency of these sources by using energy storage systems and demand response strategies, which supports the transition to a cleaner, more sustainable energy system by maximizing the use of renewable energy. Now, applied science and multi-agent approach, a study presented a multi-agent deep reinforcement learning algorithm for real-time energy management of multi-microgrids. This is one of the case study, which demonstrate how autonomous agents, each microgrid can make decisions based on local information to optimize overall system performances. And research has also shown the benefit of using DC based multi-microgrids, which includes improved efficiency and reduced carbon emissions and the system employs a cooperative optimization strategy to manage the active and reactive power flow with the multi-microgrids, enhancing economic and operational effectiveness. Now, this is one of the example of IIT Roorkee multi-microgrids where, as you could see, this is our old humanities department where do we have School of AI and Data Science. And I'm fortunate being the founding head of this Artificial Intelligence and Data Science Center, and Electrical Engineering department where most of our international projects are being deployed. So now this is my microgrid 1 and this is my microgrid 2, and they are integrated. And through our research on battery energy systems, we have considered that the future battery could be installed in the main building, in the director's office, architecture department, and earthquake engineering department. Now, the important question, it is an example of MMG for me, multi-microgrid systems. So now, if there is the battery of the microgrid 1 can be charged by the PV of microgrid 2 and vice versa, justifies the importance of multi-microgrid system of IIT Roorkee. Now, there are many challenges. It is not so easy to operate multi-microgrid systems. Integrating multiple microgrids into a cohesive system requires sophisticated control and communication technologies as well as advanced algorithm to manage the interactions between those microgrids. Existing regulatory framework and market structure may not fully support the operation of multi-microgrids, necessitating changes to facilitate their widespread adoption. Efficient operation of multi-microgrids depends on the accurate and timely collection and processing of vast amount of data from various sources, which can be challenging to manage. Now, one more future trend in distribution system analysis or distribution system today is about virtual power plants and aggregators. Aggregators are not a very new term, it's a very old term, maybe 2 decades old term, where aggregators are responsible. So, they are like a virtual energy manager. So, they contact the consumers, they contact the generating units, and then make sure they help those consumers to get energy from specific generating resources which benefit the most. So, that is the role of aggregators in the past, especially the role in North America was very, very significant before a decade. Now, today there is a term called virtual power plant, so which is not physically existing, but they act as a power plant. Okay? So, virtual power plants are advanced systems that aggregate various distributed energy resources such as solar panels, wind turbines, battery storage systems, and controllable loads into a unified centrally managed platform. The system optimizes the operation of distributed energy resources, enhance grid stability, and enable participation in electricity market. Now, virtual power plants aggregate multiple DRs and optimize their operation using advanced algorithms, and this includes coordinating energy generation, storage, and consumption to balance supply and demand efficiency. Majorly, this approach enhances grid reliability, reduces operational cost, and maximizes the use of renewable energy resources. Now, by aggregating those DRs, virtual power plants can participate in electricity market, providing services such as energy, capacity, and ancillary services. They gain visibility and can trade energy more effectively, enable smaller energy producers to compete in larger market, fostering a more decentralized and resilient energy ecosystem. Virtual power plants use sophisticated control system and communication networks to manage the distributed resources. This includes real-time monitoring and automated response to change in the grid, which improves the efficiency and responsiveness of the grid, helping to avoid congestion and manage peak demand more effectively. Now, when you integrate with the smart grid, the virtual power plants are crucial component of a smart grid. Integrating with IoT devices, AI and machine learning to enhance their predictive and adaptive capabilities. which supports the transition to a more intelligent, flexible, and sustainable energy grid. Now, few case studies: European Virtual Power Plant Project and US Department of Energy initiatives. So, various municipalities in Europe have implemented virtual power plant concept to manage their distributed energy resources effectively. These projects demonstrate the scalability and efficiency of virtual power plants in integrating renewable energy and enhancing grid stability. In case of US case study, the US Department of Energy has been promoting the development of virtual power plants to support the national grid. These initiatives focus on leveraging virtual power plant to increase grid resilience and support the integration of renewable energy sources. The major challenges are to how to go for effective operations of virtual power plants requires the integration of diverse data sources such as smart meters, sensors, grid management systems, ensuring data accuracy and consistency, which is very critical. Now, as per the market barriers is concerned, regulatory framework and market structures need to evolve to fully support the implementation and operation of virtual power plants, because today we do not have market regulation and guidelines to engage those virtual power plant concepts, which is bit of pseudo and an artificial element. So, this includes developing standards for data sharing and ensuring fair market access for aggregated resources. The quite complicated system because implementing virtual power plant involves significant technological challenges, including developing advanced control algorithms and ensuring robust communication networks. Smart grids and IoT play a very important role today in distribution systems. So, after multi-microgrids, and then we talk about virtual power plants, and let us move to IoT integration along with smart grid in the distribution systems. So, smart grids enhanced by the integration of IoT revolutionize traditional power distribution systems by enabling real-time data collection, monitoring, and automated control. This integration significantly improves the efficiency, reliability, and sustainability of the power grid. So, we can conclude that with the IoT integration with the distribution system, which supports or extract the maximum benefit out of a smart grid integration. Now, smart meters and sensors are the devices which is responsible to collect real-time data on electricity usage, grid health and environmental conditions, enabling utilities to monitor consumption patterns, detect abnormalities and respond to issues dynamically. So, it can, for example, monitor ground faults, oil and gas level in the transformers and temperature in the bindings. Communication network, which is very important. So, robust communication infrastructure including 5G and IoT protocols ensure seamless data transfer between grid components, enhancing the coordination and control capabilities of the grid. LP-WAN, low power wide area networks, technologies like LoRaWAN and NB-IoT are particularly promising for their low energy consumption and long range capabilities. Advanced distribution management systems, that is ADMS, use real time data to dynamically adjust power distribution, detect overloads and optimize grid performances. The automation enhances both safety and economic efficiencies. Now, IoT also facilitate real-time monitoring of the entire grid infrastructure. Sensors deployed across substations and transformer lines capture data on voltage, current, and other vital parameters, allowing utilities to monitor grid health, detect abnormalities, and proactively address potential issues. Now, let us focus on what kind of demand response activities we can carry out because of IoT. Now, IoT enables smart grid, empowers utilities to implement demand response program efficiently. By integrating smart meters and IoT devices in homes and business houses, utilities can remotely manage and optimize energy consumption during peak hours, reducing strain on the grid and minimize the need for costly infrastructure upgrades. We can also carry out predictive maintenance So IoT sensors offers real-time insights into the condition of grid components, enabling predictive maintenances. By continuously monitoring equipment health, utilities can identify potential failure before they occur, reducing downtime, lowering maintenance cost, and improving overall grid reliability. Now, through renewable energy integration, smart grid leverage IoT to seamlessly integrate renewable energy sources, energy storage systems, and electric vehicles. The integration allows for efficient management of distributed energy resources, optimizing their contribution to the grid and ensuring a smoother transition to a cleaner, more sustainable energy ecosystem. There are two case studies. Let us concentrate on IoT. One is Germany pilot project and Lumin energy management platforms. Germany has integrated IoT infrastructure and technology solutions to implement a smart grid project in Mannheim. This project enabled the broad adoption of renewable energy and allowed for coordinated energy consumption and production in the city. Now, in case of Lumin Energy Management Platform, this platform optimizes storage, manages electricity consumption, and facilitates the integration of PV system in homes, reflecting the practical application of IoT in smart grid. Now, what are the benefits because of IoT integration? Enhanced reliability, improved efficiency, and we can also achieve consumer engagement. But the challenges are data management, interoperability, and finally, cyber security. So, the next generation electric grid is expected to look like this. So, we will have smart grid in place, we will have microgrids, we will have virtual power plants, and then we have Internet of Energy. Okay. So, they all are connected. So, this will be the final say probably in 2030. We expect the next generation electric grid will look like of this nature. And now slowly artificial intelligence and machine learning application distribution system become very vital. So AI and ML are transforming the operation and management of electrical distribution system, and these technologies enable advanced data analysis, predictive maintenance, and automated decision making, leading to more efficient, reliable, and sustainable power distributions. So, probably through AI ML application to distribution systems, so we can still carry out predictive maintenance, load forecasting, fault detection, energy optimization, and voltage control and stability. So, advanced ML technologies such as reinforcement learning used for real time voltage control and stability management in distribution networks. Improved voltage regulation and overall grid stability, ensuring consistent power quality to our consumers. There are two important case studies. One is IEEE Power and Energy Society initiatives. IEEE PES community has been exploring the potential of ML for solving complex power system problems, including generation, transmission, distribution, and microgrid management. Efforts include developing physics informed ML techniques and performance guaranteed algorithms for power systems. So, post pandemic progress where advances in AI methodologies such as transfer learning, deep attention mechanism, and graph learning have been applied to power flow, state estimation, and voltage control, showcasing significant improvements in the operation of distribution systems. Challenges, especially data quality and quantity, integration with existing systems, and privacy and security, the certain challenges due to integration of AI and ML systems. Almost we are coming to an end, which is popularly known as blockchain technology for energy trading and security. So, this is a very, very popular concept where blockchain technology is realizing the energy sector by enabling more efficient, secure, and transparent energy trading. It supports decentralized energy transactions, allowing consumers to trade energy directly with each other without intermediaries, no intermediaries, or I think no aggregators in between. You can do the trading directly. And this peer-to-peer, that is called P2P trading system, enhances the reliability and sustainability of energy distributions. So basically we encourage peer-to-peer energy trading, which is the blockchain facilitate peer-to-peer energy trading by recording transactions on a distributed ledger. Consumers can buy and sell surplus energy directly from each other, reducing transactional cost and increasing transparency. And the main benefits which enables local energy market where consumers can choose their power sources and transact in real time, fostering a more dynamic and resilient energy ecosystem. Smart contracts, where the smart contracts automate the execution of energy transactions when predefined conditions are met. This automation ensures that the transactions are secured and tamper proof, enhancing trust among participants, and which mainly helps eliminates the need for any intermediaries. Smart contracts reduce cost and improve transactions speed and efficiency. Electricity data management is possible. Wholesale electricity distribution is also available. In case of wholesale electricity distribution, blockchain supports the automation of wholesale energy transactions, integrating IoT devices to monitor grid performance and manage energy distribution efficiently, and due to which we can improve efficiency, reduces operational cost in the distribution wholesale electricity market with real-time monitoring and data-driven decision making. Bit of case studies of these applications. So, Brooklyn microgrid, a well-known example where blockchain is used to manage a local energy market. Residents can trade surplus solar energy using blockchain, demonstrating the feasibility and benefits of decentralized energy trading systems. Now, we do have a concept of power ledger, an Australian startup that uses blockchain to create microgrids for peer-to-peer energy trading and connecting local green energy production to residential areas. This model supports the broader adoption of renewable energy sources. Then Ecoena Energy. In Spain, Ecoena Energy uses blockchain to track and verify the origin of its energy, increasing transparency and consumer trust. Once again, scalability, because gigawatt level it is very challenging, and current blockchain technologies need to address latency and scalability issues to handle the high volume of transaction in energy trading efficiently. Regulatory hurdles, for sure, regulatory framework in many regions are not yet matured enough, fully adapted to support blockchain based energy trading, which can limit its implementation and scalability. Security and privacy, certainly threat. Ensuring the security and privacy of transactions is crucial, and blockchain networks can be target for cyber attacks. Advanced encryptions and consensus mechanisms are required to protect the integrity of the system. Finally, we are into cybersecurity in distribution system. The whole world, the future era, the challenge will be destroying your distribution and transmission system through cyber threats. So, cyber security in electrical distribution system is crucial for maintaining the reliability, security and resilience of the power grid. As distribution systems increasingly incorporate advanced technologies and IoT based devices and connect to broader networks, they become more vulnerable to cyber threats. Effective cyber security measures are essential to protect these systems from malicious attack and ensure uninterrupted power supply. So, mainly actually vulnerability and risk assessment. So, which identifying and assessing vulnerability in the distribution system is the first step in cyber security. This involves analyzing potential entry point for cyber attack, such as remote access connections and then business networks and operational technologies. But it certainly helps us to understand the weaknesses in the system, and utilities can prioritize and implement appropriate security measures to mitigate those risks. Contracts, cyber security baselines and standards. Developing and adhering to cyber security baselines and standards helps ensure consistent and effective secure practices across the industry. Initiatives like the National Association of Regulatory Utility Commissioners (RUC) and the US Department of Energy (DOE) have established cybersecurity guidelines for electric distribution system and distributed energy resources, that is NRUC and UCGAO, which helps to standardize practices, enhance the overall security posture of distribution system and ensure compliance with regulatory requirements. Advanced monitoring and decisions, incident response and recovery mechanisms, and DOE's cybersecurity strategy and NRUC cybersecurity baseline are two different examples. So, in case of DOE's cybersecurity strategy, the US Department of Energy has developed a national cybersecurity strategy to protect the grid, focusing on both transmission and distribution system. This strategy includes comprehensive risk assessment and the implementation of advanced security measures to address identified vulnerabilities. NARUC's cybersecurity baselines, NARUC in collaboration with DOE has released cybersecurity baselines for electric distribution system and DRs. These guidelines provides a framework for utilities to enhance their cybersecurity practices and protect critical infrastructures. There are few challenges, especially complexity of integrations, evolving threat landscape, and finally regulatory compliances. There is one more interesting concept which is popularly known as digital twin in electrical distribution system. A digital twin in a dynamic real-time virtual replica of a physical distribution grid, and it integrates data from various sources to provide comprehensive visibility into power flow and grid behavior, enhancing the reliability and efficiency of grid operators. Real-time monitoring and simulation. Digital twins continuously gather data from sensors and devices, creating a real-time virtual mode of the grid, which enables operators to monitor performances, detect anomalies, and predict failures, reducing downtime and maintenance cost. Based on enhanced asset management, digital twins optimize the lifecycle management of grid assets, providing insight into the condition and performances. The main benefit would be improves asset reliability and efficiency through predictive maintenance and timely upgrades. Operational efficiency and safety by simulating operational scenarios, digital twins and optimizing grid operation, including load balancing and fault detection, which increases operational efficiency and safety by anticipating and mitigating potential issues before they impact the grid. Integration with advanced technology, digital twin integrate with IoT, AI, and machine learning, enhancing prediction and analytical capabilities. AR and VR applications improve field operations and training. Decision making and operational workflows through advanced simulations and real-time data analysis. There are few case studies. One is Slider Electric and ETAP collaboration. This partnership developed digital twins solutions that digitize paper-based diagrams and provide real-time simulations, improving grid efficiency, resiliency, and safety. Enel Distribution Sao Paulo. Enel developed a network digital twin in Sao Paulo as part of their urban mobility. This digital twin provides a detailed virtual model of the network, supporting dynamic and real-time data management and improving workforce operations through AR and VR applications. TERI project in Delhi. The TERI project in collaboration with Venus GmbH integrates cloud-based digital twin technology with GIS to enhance the operation and management of the distribution grid. The pilot aims to improve reliability and cost effectiveness, particularly in integrating distribution energy resources. is certainly the data integration. One of the significant challenges in developing a digital twin is integrating data from various sources such as geographic information system, enterprise asset managements, and customer metering systems. Ensuring the accuracy and consistency of this data is critical for the effectiveness of the digital twin. Scalability. Implementing a digital twin for large scale electrical distribution system can be complex and resource intensive. Utilities must manage extensive data and ensure that the digital twin remains up to date with the physical grid's continuous challenges. So these are the emerging trends. As you could see, we started from actually 1982, the first distribution system, 1986, first AC power grid installation, 1960, large, mature and interconnected power grids, 1955, first industrial microgrid, 1997, the idea of virtual power plant was proposed, and 2007, first official definition of smart grid, and 2012, when first definition of IOE, and 2020, the digital twin evaluation. So this is how actually we are progressing over a period of time. On this note, we come to an end of our distribution system analysis. Much for your kind attention. Thank you.